Thank you so much, Nino. It's a real pleasure to be here amongst so many amazing speakers and to be somehow the witness and the actor in that longevity domain that I believe is the most important revolutionary aspect of our health system if we manage to do it. My talk today will be more on the reprogramming, cell reprogramming part of longevity, because I believe, it's been established that there's a huge epigenetic component to aging. We have slowly an accumulation of methylation that prevent our DNA to function properly. And that is causing senescence and all the different aspects of aging. Somehow, back in the 90s, we believed that the DNA was fixed in a certain conformation. It was not possible to change it, but it was somehow back in the 1997 that Dolly the sheep, the first mammal, was cloned by Jan Wilmot in the UK. So what is, beside creating a full clone mammal, what was stunning was the fact that the DNA, that the cell that was introduced into the egg was actually infused by the cloning aspect of cloning fusion, was actually, the DNA was completely rejuvenated. It was going back to how it was at conception. And so that was the revolution in the biochemist and biochemistry and chemistry at the time. And we had to wait until like 2006 to have the next step of reprogramming, which was this time done by Professor Yamanaka from Japan, where he, instead of exposing a cell to the plasma of an egg, he used pluripotent genes, so the genes that are within the embryonic stem cells. He used 4 of them, which are now called the Yamanaka factors, and introduced them inside the DNA of the cell, a somatic cell. And by doing that, he completely changed and reprogrammed the cells to become almost an embryonic stem cells. It's what we call induced pluripotent stem cells. They are not fully embryonic, but they behave like one. The key is that somehow by introducing specific genes inside the DNA of that cells, it was affecting or producing proteins that were affecting the epigenetic of the cells, therefore taking them back to a young stage. The next step, and that we all know about that one, 2012 and 13, a major publication about the CRISPR-based genome editing. At that time, it's clearly a modification of the DNA. So you're able to either remove pieces of the DNA that is damaged and replace them, or enhance the DNA so that it expresses different things. So we reprogram cells deeply into the genetic base. That is obviously affecting the epigenetic as well. So these are all the different major steps, I would say, for reprogramming. But the one that made me the most excited about somehow, it was back in 2020, when Professor Sebastiano from Stanford published that the results of these studies were using all kinds of different somatic cells. He introduced the Yamanaka factors in the form this time of microRNA inside RNA messenger inside the plasma of the cells. So it was not affecting the DNA, the genes of the cells, not introducing any with retrovirus or anything, only the RNA were involved inside the plasma. And by producing specific proteins, the protein affected the epigenetic of the cells. And what he was able to do is bring back old cells to a very young stage, a very young state. And instead of taking them back to a pluripotent state. So somehow, it was like closing the circle. Somehow what was done in cloning back in the 90s, not really knowing what was going on, just putting a cell into an egg and fusing and witnessing this reprogramming of the DNA. Somehow Sebastiano did it by selecting a specific microRNAs. And that reprogramming of the DNA is, I believe, one of the important and key factors that we have to use in our search and in our hope for longevity. And that's what we are doing at Stemaid, turning back the epigenetic clock with non-invasive pluripotent signals, because these pluripotent signals have the capacity to remove all the epigenetic markers of age in our body. The keys on how to use them. Obviously, we cannot add all these genes or all these RNA inside the plasma of the quadrillions of cells that we have, but we can expose the cells to these pluripotent RNA. And that's what we've been doing, using embryonic stem cells or pluripotent stem cells for the past 14 years. Clinically, I would say for 9 years now. These cells were given to us back in 2004 from an IVF clinic. When parents want to have children, they produce many different embryos, and when they have children, the extra embryos are discarded. So one of them was donated with the consent of all the different committees, and we have been using them since then. The important part of what that means is that these cells have been growing since then. So we only use one line, and that line has been used, so repeatedly, so that we know what to expect and not to expect from them. And I'll take a parenthesis there, because it's one of the many positive aspect of using embryonic or pluripotent stem cells, is that they live such a long time, so that we know exactly their DNA and what microRNA they are expressing and enzymes. While when we use adult stem cells, we cannot expand them for years, so maybe 5 or 6 passages in the cell's growth. And that means that each time there's a new set, a new batch, and a new set of DNA as well. And therefore, all the RNAs and enzymes that they produce are different each time. So if you hear some people saying, oh, it doesn't work, or I got some mesenchymal stem cells, it didn't work, it may not mean that mesenchymal stem cells don't work. It means that it's a different batch that was not appropriate. So we're somehow lucky to be working with that type of cells. They work. There's another myth that I want to bust here. People are believing, a lot of our clients are thinking that when we give them stem cells, these stem cells are going to stay in the body. You don't want them to stay. That's what people are, scientists are saying. If they stay, they become teratoma, because the DNA of these cells is different from the DNA of the recipients. And therefore, the moment they differentiate, because it's the fate of pluripotent stem cells, they will become foreign cells and recognized by the immune system and removed. So we deliver these cells only to non-immunosuppressed recipient to make sure that they are removed properly. Cells do not stay and replenish, but they express their exosomes, and the exosomes are somehow tailored to the terrain of the recipient. If the cells are screaming injury, like a previous speaker was saying, like the senescent cell screening injury and then it's inflammation. Well, the pluripotent stem cells in the body will express more anti-inflammatory factors. If there's a screen for fibrosis, it's going to be anti-fibrotic, or there will be all the senolytic and all that. So the list, when we do the analysis of the exosomes, the 700s or 800s entries of proteins and RNAs, enzymes, all kind of different molecules that are working synergetically and targeting senescence and fibrosis and wound closure. We have amazing results in helping wounded individuals, or restoring or repairing the blood flow, the cardiovascular system. One of your speakers were talking about the need to address atherosclerosis, and I think it's one of the positive side effects of using these cells. They're very unique microRNAs that we don't always know what they are doing, but what I believe is important to take also from our experience is that by removing specific protein from these secretome, all these exosomes, we might be able to show what that protein is doing and helping. And that's, for example, the work of Juvena on the protein that is helping the muscles, and protein extracted from the exosomes via pluripotent exosomes. And that's wonderful. It's somehow by combining this protein with all the different other secretome of the pluripotent stem cells, we have a more synergetic effect. And I will take that example. I mean, I'm going to show a few examples of things that make us excited at Stemaid daily. That's a story of a young man suffering from muscular dystrophy. When he arrived, he's probably like 25 and almost having difficulties to breathe and even to sit because he won't be able to stand up. So quite advanced. His CPKT was at 700, almost 800, CPKMB at 100. So clearly muscle damage. And he couldn't stay more than a week. So we measured after a week and all these values were down, not in range yet. When he had that tested again a few days ago by his doctors back home, these values kept decreasing. And of course, he's doing better, he's breathing better and all that. What is interesting here is that muscular dystrophy is known as a genetic disease, but somehow by using our pluripotent cells, we were able to signal the epigenetic of the disease. And somehow I was expecting, values to go back up because the genes, we cannot modify the genes, but somehow we are modifying the epigenetic of it so that this gentleman is able to breathe better. And so we have lots of those evidence in the muscles, in different organs. That's a liver function test that man came with bilirubin at 12, and he was on the liver transplant list, but couldn't get it because of his past history of drinking. So he came to us in 2 weeks. The bilirubin was down to 4, and all the AST, ALT liver enzymes were dramatically down. 6 months later, he came back for a boost, and his AST, ALT was still low, and his bilirubin was at 2.9, and he's still around 2. So it's not completely fixed, but it's livable. He's out of liver transplant list and functioning. So these We can show, the repair in all the different organs like that. We do see lots of different chronic conditions. Tumor markers, not very elevated. I'm not claiming that pluripotent stem cells are a way to treat cancer, but look at for example, CA15-3, slightly elevated at 60. No, I'm not saying that's a way to measure cancer, but it's definitely showing some imbalance in the breast, and reduced within a month. It was reduced to 43 and stable down around 40 now. These are values that we see all the times, and where we have a clear indication of overall system that is overloaded, and that the cells are fixing. We talked about telomerase earlier in that with Bill Andrews being the expert on that, and these are the results of a very early test that we were running back in 2013. At the time, we were giving 5 million stem cells per month. And so that's over 12 months. We monitor the telomere length, and we had an average of 14% increase just with 5 million once a month. Today, we are giving 20 million pluripotent stem cells daily for weeks for chronic condition and all that. So, and we have other measures that we're putting together, showing that it's actually, especially for individuals in their 80s and up, where the telomeres are really, really short in the last quadrant, of the test, we can actually put them back into a less dangerous level. So these are small examples of what we observe besides the whole the overall health of these individuals, and how we change their the capacity or the quality of life, and hopefully the longevity, which is what we want to demonstrate as well. But the reason why is because these pluripotent stem cells express paracrine signals to all tissues because of these full reprogrammed or fully open program of epigenetic. All the genes are able to express, and therefore we can reach most of the tissues. The other thing that I'm very excited about is the capacity to do specialized stem cells. I mentioned that pluripotent stem cells express and signal repair in the body, and they are evacuated afterwards. Some of them can stay if they do have the recipient DNA, and that's what we have been able to produce for the past 5 years with one skin sample. We are able to clone them, so expose them to the plasma of an egg that we produce by CRISPR. So somehow we are using one skin cells to produce an egg, and by then fusing it after enucleation, so that we have, as a result, a small blastocyst that carries the DNA of the recipient and the mitochondria of the recipient, and all that fully at the pluripotent stage. After that, then we can use them. These pluripotent, autologous pluripotent stem cells will signal, like regular pluripotent stem cells, they will signal repair, but they will also replenish the stem cells niche of the individuals who are receiving that, or restore and replace senescent cells. So somehow it's what we are the most excited about at this time. We already have 74 lines for 74 different individuals benefiting from that with great results. Indications of these pluripotent stem cells, brain damage, Alzheimer's, dementia. We have ongoing studies for that. Diabetes, somehow removing all the injuries or the insults of food excess and environmental abuse. COPD, restoring the lungs, cerebral palsy, young children, recovering developmental problems, but somehow each one of these diseases will require a certain amount of time with us that we treat 1, 2, 3, 4 weeks, or sometimes we have to return. So stem cells are not a magic bullet, but they have all these exosomes expressing repair that are touching all the cells in our different organs, which are themselves younger and producing different exosomes of rejuvenation, which somehow creates what we call the butterfly effect. So by receiving 1 week or 2 weeks of treatment, it could actually, we can see improvement for 2-3 months afterwards. And among the indication, obviously, aging, which is our ongoing passion. And we are scheduling actually a fully double-blind, placebo-randomized study that I hope to be presenting in my next talk. One last slide, just to say, if for anyone having fear, because if you read about pluripotent stem cells or pluripotent genes or using a specific one Yamanaka factor that can do some cancer growth and all that, not only didn't we see any of those effects after 14 years of application with different pace and amount and all that, but they are indication, although we don't have that data at Stemaid, because that would be ethically impossible, but they are evidence that these embryonic stem cells can prevent cancer growth. And that was done on mice that were injected pluripotent stem cells for a certain duration, and after that, given cancer cells. So while in the control group, the cancer cells were developing like they know how to do within the body, the mice that received pluripotent stem cells before didn't develop any cancer after being injected cancer cells, so they destroy them. That is even more encouraging if you think of it, but it's not a surprise. Somehow there's an intelligence in those cells that we can already harness and benefit from in combination of all these different things that have been done. I mean, I believe in quercetin, rapamycin, and everything. That is the combination of these pluripotent stem cells with what is also developed right now, and healthy lifestyle and healthy environment and healthy thoughts. And that's that I believe that we can go a long way. So that if anyone wants to reach me, you can reach me there at stemaid.com.